Okay, so actually numerical integration problems can also be solved using the Monte Carlo simulation. Later we will have a special lecture and chapter on Monte Carlo simulation and how we use it in option pricing. But here we have a small part. So basically, let's consider the integral over 0, 1. So if we are trying to integrate this g of x over the unit interval, actually this can be done by generating the uniform numbers, because notice that this dx, this integration, actually this is same as the uniform density. So actually you can consider that we are actually integrating this gx with respect to the uniform distribution over the unit interval. So with this interpretation of the same expression here, actually we can just calculate the uniform random numbers. We can generate these numbers and evaluate our function g using these ui values coming from the 0, 1 uniform distribution. And then we can just average these function evaluations with the number of uniform numbers that we have generated, which is n in this case. So actually the strong law of large numbers guarantees us that basically the average value of this g will converge to the original integral I with probability 1. Okay, so basically as we sample more and more uniform points over this uniform distribution, we are guaranteed that the average quantity here, the sample average, will converge to the true population mean, which is this expectation actually with respect to the uniform distribution. So we can verify this easily with some examples. So you can see that here we are trying to integrate exponential function over 0, 1. So for this problem, we can actually calculate what's the analytical solution. You can see it is 1.71. And we can test it actually easily by taking the sample average. So basically what we are going to do is we will generate, let's say, 100 random uniform numbers. We will evaluate them with the exponential function. And then we are going to calculate what's the sample mean. So it is exactly what we explained in this equation 25. And we can verify whether what we get is really getting close to the true solution or not. Oops, I made an error here. This should be, of course, 100. So we can see that by generating 100 uniform numbers, I get somewhat close, but it's not that close. So if we want to improve the accuracy, what we need to do is increase the sample size. And you can also notice that every time I run, since MATLAB is generating brand new set of uniform numbers, so basically the result will change. So if we make it really bigger, we can notice that our result gets much better. So we have the 3 digits now same. So of course it would take quite many simulations to get a very accurate result. So that's maybe the kind of disadvantage in Monte Carlo, is a relatively slower convergence rate for low-dimensional problems, like in this example, which is just a one-dimensional integral. Obviously, for this type of problems, the quadrature methods, numerical integration, will be converging much faster. But notice that if we have high-dimensional problems, then actually Monte Carlo will be probably your only choice, especially if you are trying to integrate, let's say, 5 or 10-dimensional integrals, then Monte Carlo will actually pay off.